Hi, I'm Ben-Yaakov. This presentation is entitled MOSFETs Gate Resistors. There is a relevant video to this presentation. Here's the link to it. It's Power MOSFET Drivers. I'm going to put the link at the page of this YouTube video that you are now watching. There is a disclaimer here that the specific driver shown in this presentation is just an example intended for educational purposes. There is no recommendation or endorsement implied. And also it should be noted that other manufacturers offer similar devices. So what's the outline in brief? First of all, I'll cover the need for gate current. A detailed discussion on this is in the video that I've referenced. And then how much current do we actually need? Slow turn on and fast turn off, current setting by gate resistors, the power losses of the resistors, characterization of commercial gate drivers' current capability, and driving MOSFETs in parallel. Let's start by looking at this half bridge or synchronous buck converter. We have a lower transistor MOSFET, higher transistor, a driver, and here is what is really happening. We have a driver, a resistor limiting the current, and let's consider the turn on of this Q1. As we turn it on, the current is first maximum because the voltage here is 0, here the voltage is 0, and then as the voltage builds up, we get to the threshold voltage. We stay there for a while because at this point we see here a large capacitor. This is the so-called Miller capacitor, Miller effect capacitor, or you can look at it this way. We have to charge this capacitor as the voltage of the drain goes down to the source, go down to 0, and all this way the gate voltage is about constant, about the threshold, and we have about a constant current. And then the current is required to finally charge up the capacitor to the final value, and then the current tapers on. And during the on time, or the rest of the time, there is no current to the gate because there is a insulation here. It's a MOSFET, it's a metal oxide, which is non-conducting, of course. Only during the turn on and off, we see these short period of current. Looking at it more closely, here I'm showing the charge that is required. Usually you'll find it in data sheets of MOSFET. So what we see here that at the beginning the charge is building up, the voltage is going up to the threshold. This is the time that a transition occurs. This is the time that the VDS is going down. And then we have about a constant current. And then the current tapers off while we are still charging the gate up to the maximum output of the driver. And at that time, VDS, of course, is low. Another issue that we have to deal with is the reverse recovery of a diode. In all PWM topologies, we'll find that in one instance of the turn on, we have a situation in which, for example, I'm showing it here. Before this transistor is turned on, this upper transistor was on, current was passing through the transistor, and as we have the dead time that we need in order to avoid a shoot through, the current will be passing through the diode, and then as we turn on the transistor, we are actually turning it against a conducting diode, and then we have this reverse recovery effect or phenomena. Here is the forward current of the diode, and then it goes down, and eventually it actually reverses, and we have a high negative peak in the diode, and it is a positive current in the drain. We see it here. This is the current coming here during the reverse recovery. Now, as it turns out, the magnitude of this peak is a function of the rate at which this goes down. The faster we go down, the higher will be the peak. So therefore, we would like to slow down the turn on while it is, of course, slowing down the switch, but still it is avoiding the high reverse current of the reverse recovery. which are causing losses in EMI, electromagnetic interference. So this is another issue we have to consider, and this is why normally we'll find that a good design will have actually two resistors, one for turn on and one for turn off. The turn on will be a larger resistor, smaller current, slower turn on, and here we have a smaller resistor with a higher current. The diode is actually providing the separation of the two paths of the current. So how much current do we actually need? We have to supply a certain amount of charge. It takes some time to supply it. The larger the current, the faster will be this duration. So we can write here that the delta Q needed, and let's consider the total Q, gate charge, is, let's talk about a current during, the average current during this period, times delta T Ig, or the current times delta T is delta Q. Therefore, the amount of current that we need is this delta Q, which is given in the data sheet, divided by delta T that we wish. So suppose the delta Q is 100 nanocoulomb, and we wish to have a transition of 100 nanosecond. This brings about a requirement of a current, gate current of 1 amp. You see that this is not insignificant. We are talking about fairly high current. This, by the way, 100 nanocoulomb is for a fairly hefty transistor. So we have now the two resistors. So let's consider now the case of turn on with a driver. Now the driver has an output resistance. We're putting here a resistor. So the current that we are going to have here during the crucial time when we have the voltage of the gate to be equal to the threshold voltage, it will be the VCC of the supply minus VT over the total resistances. So this will be the current we are going to have during the turn on. Now during turn off, what we are doing actually is discharging the charge or the voltage of this capacitance. During the threshold, the holding period, we have a voltage here, constant voltage, and we have a current here, which is determined by just the resistances and the voltage drop of the diode. So we have VT minus VD, the diode, divided by these two. So this will be the current that we are discharging the gate during the turn off. And as we said, we'd like this current to be higher for the reason I've stated. Now the charging and discharging of the gate capacitances entails some power loss because current is passing through these resistors. As it turns out, and we know that when you charge or discharge a capacitor, of the total energy that you supply, half of it will be charged or stored in the capacitor, and half of it will be dissipated in the resistor. Now the total energy that is consumed from the power supply will be, this energy will be the voltage here times the total gate charge, and therefore the power dissipation of the system will be the energy times the frequency. This is the total resistors plus capacitances. Half of it is going to be dissipated by the resistors. So let's take an example here. We have a certain amount of charge that we need. This is the energy, this is the power. Half of it is going to be dissipated by the resistor, and then it's going to be splitted between these two according to the magnitude of the resistor, the value of the resistance, because the same current is passing through them. So out of the half of the total energy coming out of the source, we can find what is the power dissipation of this resistor and of the driver inside. Let's take a numerical example here. Suppose again it's 100 nanocoulomb the gate, supply of 12 volt, switching frequency 100 kilohertz. We find that for this particular case, the total power coming out of the source is 120 milliwatt. 60 milliwatt is going to be dissipated by the resistors. Now, this is at low frequency, say 100 kilohertz. It's fairly low, but obviously it's linear with the frequency. So the higher the frequency, the higher will be the dissipation. But the problem is that we are passing high current through this resistor, so one has to choose high current pulse resistor. That is, there's special types of resistors that are capable of handling high current pulses. So it's very important to choose them, otherwise there might be a problem that the resistor would sort of disconnect. Now, during turn off, the same amount of power is actually dissipated. So the energy dissipated by the resistor is actually twice the value that we found here. Okay, so one has to take into account that both during the turn on and turn off, we are losing all the energy. In fact, you might say that out of the energy that came out of VCC, all of it has been dissipated by the resistor. That is, all of this is dissipated by the resistors, because half of it is going to be dissipated during turn on, and half of it is going to be dissipated in turn off. That is, energy is coming out and then vanishing or dissipated into the resistors. No energy, of course, is dissipated here. So all the energy from here is dissipated by the resistor. So this is the total energy, in this case power, dissipated by the resistor. Let's have a look now at the typical data that manufacturers are providing at the data sheet. This is a driver by Silicon Lab company, and there are two models here, a hefty one and a lower power one. Let's look at the higher current one. This is this series here. So we see that the resistance, output sink resistance, is 1 ohm. The output source resistance is 2.7. Again, taking into account that we need a higher current at turn off and lower current at turn on. And then the specified maximum current or typical current during turn off is 4 amp, and the output current is 2 amp for the turn on. Now, in the datasheet, we also see how these were actually verified or measured. So we see here the portion of the turn off. Okay, we have here something that is emulating a gate, constant voltage, 100 microfarad during the pulse. It's about constant voltage. Here is 8 volts, so we are talking about like a threshold of 8 volt. And then we have the Schottky diode, and then it goes down to ground. So we know that for the high current type, the internal resistance here is 1 ohm. So approximately from this circuit, based on the 1 ohm, we should have expected up to 7 amps, sort of approaching 7 amp. And while the datasheet sort of says that the typical value is 4 amp. So this is pretty consistent for the two type of parameters that are given. Now for the turn on, there's also a Schottky diode because this is a voltage source here. And in this case, we have a 15 volt here. So it's 15 volt minus the voltage drop on the diode, minus 5.5. The threshold now is assumed to be 5.5 volt, so that you have a higher current. And then it comes out to be 3.3 if we assume a 2.7 ohm on resistor or sourcing resistor, while the datasheet talks about 2 amp, which is then very consistent and everything is fine. Now, what about the case that we would like to drive a number of transistors in parallel? Now, in many cases, we'd like to put transistor in parallel to handle a much higher current than the individual transistor. In this case, what has to be done is to put for each one of them this network for charging and discharging, and not connecting all the gates together with one network here. Now the reason is that the threshold voltage is not a very accurate voltage. There's a spread of the values, and it's also temperature dependent, so that you might have a case in which the threshold voltage of one transistor is different from the other transistor. So for example, if you in the turn on stage, the transistor with the lower threshold will start conducting while the others will not. And this is very bad because all the current will be passing through this single transistor. So therefore, you would like to put these resistors such that the voltage drop of the resistor is appreciably larger than the deviation that you would expect, such that if this is a certain voltage here, small deviation here relatively to the voltage here will not cause a large difference in the current between, say, this resistor and this resistor. We'll see this in a minute. So let's take an example here. Suppose we have a power supply, VCC, there is the output resistance of the driver. I'm talking now turn on. I have a number of transistors, I'm assuming 4 transistors. So we have all these in fact in parallel, and I'm assuming the voltage here is high enough, so there is sort of an average threshold voltage here. So the total current that will be coming out of the driver will be VCC minus VT, the voltage here, divided by the total resistance, the source gate resistor divided by N being 4 in this case. Now, for this particular driver, we know that we can get 2 amp out of here during the turn on, and therefore we can get 0.5 amp per transistor if we have 4 transistors, because the current is now will be distributed here between them. Now, looking at a numerical case, suppose we have a 12 volt. This is the internal resistance. Here is the resistor divided by 4 because we have 4 transistors, and I'm now going to calculate what should be this resistance per transistor such that we'll really utilize the driver to the utmost value of 2 amp. Okay, so the difference here is 6 volt divided by 2.7 plus this resistance, and it comes out to be 1.2 volt. Now, if this is the case, we have a problem here because the voltage drop on the internal resistance here, 2.7 here, the voltage drop is already 5.4 volts. So therefore, the voltage at this point, this is at the output of the driver, this is the inside of the driver, this is the output, is already 6.6, 12 minus 5.4. So we have only 0.6 volt difference, and this is not good enough, because if the threshold voltages are changing, then we'll have a case in which one transistor sees different current, and this is not very good. We don't like that. So therefore, we have to remedy it, and one possibility, for example, in this particular case, is to increase the voltage to 15 volt. If I increase the voltage to 15 volt, the voltage here now increases because, again, this is 2 amp times 2.4, it's 5.4 volts. And therefore here we have 9.6. And then we have here 6 volts, so we have 3.6 volts, which is pretty good. And therefore I can find that in this case I need a resistance of 7.2 ohm, each one here, and then I'm going to have total of 2 amp here and 0.5 amp to each transistor, which is again using or utilizing the driver to the utmost. Now there is another issue that I like to point out to, and that is in the case of a half bridge, and say if you have a driver, half bridge driver, and there is a midpoint here of the driver, there's a midpoint between these transistors. I'm talking about the case of, say, high power, a number of transistors. As it turns out, Due to leakages, I will find here a negative voltage, a negative spike during turn off. And this is again caused by the leakages. I'm not going into all the details. You can find it in many application notes of vendors of these drivers. But it is an annoying phenomena because this negative going pulse can actually damage the driver. So in order to protect the driver, one way to do it is to put here a resistor which is sort of limiting the current that you have here going through this process. Now once you put this resistor, and this is now our issue here in this presentation, it actually becomes part of the gate drive because during the turn on, actually you are passing all the current through it, and during the turn off you're also passing the current through it. So therefore you have now an extra voltage drop here, so you have to be very careful not to increase this resistance very much, otherwise you will lower the current of the gates because of this voltage drop here. Let me now finish with this remark that not all gate drivers have a MOSFET output stage, which is characterized by RDS on. Some have a BJT output stage, and the output characteristic is different because there is a voltage drop rather than a resistance. So this is something that has to be taken into account. So one has to very carefully examine the data sheet to see what is the type of driver that he's handling and what is the type of element that are at the output, what's the characteristic of this particular driver. So this brings me to the end of this presentation. I hope you found it of interest and perhaps it will be useful to you in the future. Thank you very much.